Welcome to Shormann Calculus, and Lesson 1 is titled Number, and in any Shormann math course there's 10 major topics. Some are emphasized more than others. So there's number, there's ratio, geometry, there's 10 of them altogether. Calculus is one of those. Obviously in calculus, in Shormann Calculus, then the calculus topics will be the main emphasis. Those are your priority here. So a lesson like number is lower priority, but nevertheless still important. And if you completed Shormann Pre-Calculus or another Shormann math course, you may remember learning that mathematics is deductive in nature. It's about applying rules, and so that means the focus is to learn the rules and then apply them to the study of God's creation by doing stuff. So science, doing science experiments, engineering, cooking, making things. And because math is deductive, the first quarter of any Shormann math course is designed to introduce you to fundamental rules or review them, things that you'll use for the rest of the course. So here in Lesson 1, our emphasis is number. Numbers are abstract ideas. That means they can be used to describe an infinite number of situations. So like here we have two hydrofoil surfers. We can use number 2 to describe the number of waves that they're being surfed right now, the number of surfers, the number of hydrofoils. So, and a picture can help us understand number, but a picture like this can also help us think about just calculus in general. Calculus integrates a lot of different topics together, and things that you maybe didn't know mixed together before, like a hydrofoil and a surfboard. Maybe you've never seen someone flying above the water on a hydrofoil surfboard before. So just get ready in calculus to combine things that you are maybe familiar with in different ways that you hadn't expected before, and that are actually pretty awesome when you combine them together. So before we get into doing some review problems and example problems, we're just going to spend some time introducing the course and talking about what mathematics is. You can take notes on this. You don't have to write everything down that's on the screen right now. That's not the point here. But the main thing is to listen, and if there's something in particular that you want to try to remember, then feel free to write that down. So the fact that you're taking a calculus course, that means you're smart. And in fact, by the time you're finished with Shormann Calculus, you definitely will learn more mathematics than most people in the world will ever learn. And so that's pretty amazing. And because of that, I think there's something you should be proud of. There's more, though. I think you should consider Proverbs 15:33. So again, you don't have to write the whole verse down. If you want to, you can. Or just write Proverbs 15:33 for future reference. And that says that the fear of the Lord is instruction in wisdom, and humility comes before honor. So humility, that's a big deal in mathematics. We're not doing calculus to tell everybody how smart we are and how much smarter we are than them. That you are going to know more mathematics than most people in the world. Be humbled by that. Be glad about that. Think about how God would want to use that knowledge that you have for His glory. So use that knowledge not in a prideful, self-centered way like a power-hungry weirdo or something, but use it to have an opportunity to be thankful to your parents, to God for allowing you to understand amazing things that others don't know about, and just an attitude of gratitude, kindness. How can I help others with this knowledge? So part A is about what is mathematics, answering that question. And before we start talking about number, let's look at some ways of defining mathematics. And mathematics is many things wrapped into one. It's not easy to have just one definition for it. And so here's a few famous mathematicians have written, famous math teachers have come up with over the years. And again, you don't have to write all these down, but at least know where to find them here on this lecture or in your reading assignment. And so Leonard Euler, he said that mathematics is the science which investigates the means of measuring quantity. Alfred North Whitehead, he said that it's the foundation of exact thought as applied to natural phenomena. And W.W. Sawyer, he said mathematics is the classification and study of all possible patterns. A study of space and quantity, that's what Morris Klein said mathematics is. You can see similarities in their definitions, you can see differences. All of them are right about their definition, though. all of those definitions are okay. Alfred North Whitehead, an American, he said that mathematics is abstract, which means it deals with properties and ideas of things just because they are things, regardless of how we feel about them, any sensations we might connect with them. So thinking about that picture of the hydrofoil surfers, it doesn't matter how I feel about surfers riding above the waves on hydrofoils. If there are two of them in the photo, then there are two. No other value works in that photo. So if I wrote like there's 5 surfers riding hydrofoils in that photo, you'd immediately think that either I made a typo or I'm lying about this picture here, because clearly there are 2 surfers, not 5. So math helps us know that if we search for truth in something, we can often find it. Because math reveals truth to us, it naturally leads to the question, is there a source of truth? In other words, mathematics points us to God. And only the fool says in their heart there is no God. The deeper you understand math, including calculus, especially calculus, the more foolish such statements will become. So if you haven't done so already, maybe before you get too much farther into the course, you should take a moment to stop, pray, ask God to lead you through Shormann calculus. More importantly, if you have yet to accept God's saving gift of faith, as is described in Ephesians 2, 8, and 9, and elsewhere in the Bible, please consider doing that right now. And that's not like a sales pitch for Jesus or something, or a requirement to pass the class or anything like that. But I'm going to be sharing some good news with you, things that I think are good things, like a calculus course that will really benefit you. I think this will, and I think it's a good thing for you to do. I think believing and repenting, being baptized in the name of God's Son, Jesus Christ, gave his own life for the remission of sins. And when we do that, we'll receive the gift of the Holy Spirit. That's what it says in Acts chapter 2, 38 and 39. You are totally 100% welcome not to do that, of course. That decision is not between you and me. It's between you and God. But here's what I believe. I believe when we do trust Christ as our Savior, we can know more things. Not everything, but more things about our origins, about what we're supposed to do, be doing right now, what will happen in the future, eternal life. It helps us see the unity and diversity found in the Holy Trinity, where Scripture proclaims that God is Father, Son, and Holy Spirit. So we see what is general. Think of that as God. In what is particular, the Trinity, Father, Son, and Spirit. What is unchangeable in what is changing. So the Bible says that there's one God, and He is also 3 individual persons, Father, Son, and Spirit. How can one thing be 3 things? Well, that's what math is. We'll talk about that more here, but this attribute of God, this unity and diversity, and other attributes like his divine nature, his eternal power, those are revealed in mathematics. Romans 1:20, it says his invisible attributes like these are clearly seen in creation, so that we have no excuse for denying his existence. So the word Godhead, that's also used to describe God's divine nature, reflecting the Trinity, which in turn reflects God's perfect example of unity and diversity, this attribute that is important in mathematics. In Christ, we see the fullness of the Godhead bodily. That's what Colossians 2:9 says. And that means that Christ is truly divine, but also truly human. God's divine nature is also abstract because he exists apart from our feelings about him. So, understanding some things, but not everything necessarily about a concept that requires humility, patience, joy, perseverance, and prayer. And whether you're a Christian or not, think about your attitudes of pride, of arrogance, impatience, general grouchiness. Those are not going to make learning math easier. So to help you get a better understanding of things that relate to the concept of unity and diversity, take a look at this table here. And before you begin any lesson, watching a lecture, you should look at the reading assignment and especially take a look at the rules and definitions. Go back to those during the week and try to memorize those. But you can also move quickly through the reading assignment just to see what it's about, and maybe you've already noticed this table already when you did go through the reading assignment. But things that have this attribute of unity and diversity, of course, God, and the diversity part would be the Trinity. Unity is Jesus Christ. Diversity is that he's fully divine and fully human. And then some other more mathematical related things. The general is related to unity. Diversity is particular instances. Abstract and concrete. Again, concrete examples of things, not like the material concrete, but real examples is what that means. So abstract are kind of like the idea, concrete are specific examples. So there's a diverse number of specific examples of a particular abstract idea. Eternal and mortal, infinite and finite, continuous and discrete. That's a big one in calculus, where you have a continuous function and you think of breaking that function into individual discrete pieces. And the one and the many. Christianity is about a relationship with God, not a religion, but sometimes that word's just used to describe a belief in God. So of all the religions that are out there, Christianity is the only one that describes this attribute that the world has of one and many, how one thing can also be described as many things, how one cell can be described as many parts within it, how one man could be a dad, a husband, an employee, an employer. This attribute of unity and diversity, of the one and the many, it's all around us. So as far as things to write down right now, here's an important one. Mathematics is considered the language of science. It's a tool for studying God's creation. That's a way we think about it in Shormann math. So God, he has an abstract nature. It makes sense that he would design our brains with the ability to use an abstract tool like mathematics to help us learn about how his creation operates. Human beings, no other organisms. Think about that. There's no other plants or animals, anything that's created in God's image, like Genesis 1:26 says. He designed us to be creative like him. As a famous scientist, Johannes Kepler, said, when we study God's creation, what we're doing there is thinking God's thoughts after him, and that gives us and no other organisms the ability to manage his creation, to wisely use the resources. Mathematical tools, because they are abstract, they supply just what is needed for a biblical and therefore scientific description of creation. And these tools, they'll help you be the best you can be at using and managing God's creation. And I would assume that you'd want to be a good manager of his creation as opposed to a bad one. And therefore you'd want to be able to do what you need to, and part of that is just understanding math, thinking mathematically about a lot of different things. So we'll finish up here with our introduction to what mathematics is in part A with another definition here. This is one we use in Shormann mathematics. Maybe you remember this from a previous Shormann math course. Mathematics is a language of science and a God-given tool for measuring and classifying pattern and shape. So measuring is a big deal, classifying, organizing things, describing them. Looking for patterns in God's creation, whether that's a change in speed over a change in time, or a particular volume or area or perimeter, things like that. So let's move on to part B on a brief history of number. And we're still not doing any example problems yet, and that's okay. It's good to just get some fundamentals down, get a foundation down before you get going. Learn about a subject before you just jump right in. So a number is an idea. That's what John Saxon said about a number. So it's an abstract idea that applies in an infinite number of situations. We'll be talking about infinity a lot in calculus. We use numerals and symbols representing the idea of numbers. So numbers, like math itself, they're abstract rules. So think about the two surfers riding the hydrofoils. That two-ness, that's an idea that can be applied to a variety of situations. We already talked about some of that. Two surfers, two nostrils, two flags, two waves, and so on. It seems strange that one thing, a 2, can describe many things. It's strange, but it works. The abstract nature of our Creator, one God, three persons, that reminds us we should not be surprised to find that aspect of His creation, and that it has many aspects of His creation have abstract qualities too. So looking back at history, the Egyptians and Babylonians, 2500 BC to AD 260, that's basically post-flood. Not much is known about the pre-flood world. After the flood, Babylon grew, later to be dispersed by God, and the oldest known mathematical documents are from the Babylonians, and it's difficult to say what knowledge was transferred to the Babylonians from the pre-flood world. But some things we know about the Egyptians and Babylonians is that they had a system of weights and measures, they had a calendar, ability to calculate things like perimeter area and volume, financial and commercial methods for raising taxes, and trade purposes. One reason mathematics stagnated for them is because they worshiped the creature, not the creator. But why would that matter, that they worshipped the creature instead of the creator? How would that affect mathematics? Why can't I just go worship a duck? And why would that have a bearing on my ability to do math? Well, mainly because creatures aren't God, and they don't write instruction manuals on how to live your life and things like that. And that hopefully isn't a surprise to you, that if you worship a creature like a duck, the duck isn't going to say, hey, just ask me, and I'll teach you great and unsearchable things you didn't know. No, creatures don't say things like that, but God does. That's actually Jeremiah 33:3. And if you look back at history, you'll see how learning, not just math, but learning in general, it stagnates when people worship creatures. It flourishes when individuals, cities, nations, they surrender their lives to Christ. Again, this is a brief history of number. We're not covering everything in history. So just some interesting groups and individuals like Pythagoras. He's credited with developing the Pythagorean theorem, lived around 400 to 500 BC, and although the Babylonians, they also knew about the Pythagorean theorem, he's just credited with developing it, publishing about it. Pythagoras, he had a religious following of people. They worshiped the reflection of God. They worshiped mathematical order, and they appreciated that, but they worshiped that instead of God himself. They worshiped numbers. So that's very strange. They believed the universe could be explained by the set of counting numbers, whatever that means. The cult, the Pythagorean cult, it disintegrated when they discovered the simple fact that they could not, should have a square root 2 right there, they could not represent the square root of 2 by a fraction of 2 integers. We'll talk more about irrational numbers in lesson 2, but their cult disintegrated because of the square root of 2, which again is very strange. The Greeks, from around 600 BC to AD 450, so about 1,000 years, they did much great work on human reasoning, but they went too far in idolizing our brains and what we could think of. So if something didn't make sense, like infinity, or like the square root of 2, like irrational numbers, they basically just ignored them. And that's why they shied away from arithmetic and algebra and focused more on geometry, on making shapes with a compass and a straight edge, where they could make a triangle like this, so side 1, but they didn't have to worry about why this side was equal to the square root of 2. Some other groups, Chinese, Inca, Mayan, American Indian, over about a 3,000 year period here, supposedly they were isolated from the mainstream of mathematical development, but nevertheless they had their own decimal numeral system, so maybe they weren't as isolated as we think they were. But that shouldn't really surprise us that they all had decimal numeral systems, since we all had the same creator. He designed us to reason through things. Their numeral systems also display vestiges of their Babylonian ancestry because of the widespread use of the sexagesimal or base 60. numeral system, and that means like 60 seconds in a minute, 60 minutes in an hour, 360 degrees, which is 60 times 6, 360 degrees in a circle, things like that. Hindus and Arabians, last group we'll look at here, the Hindu-Arabic numeral system that we use right now to identify numbers, that's named after the Hindus, who probably invented it, and the Arabs, who passed the system on to Western Europe. They also invented negative numbers and the numeral 0. So here we can see it in the Mayan system there, who even though they were a continent away, they developed the number 0 about the same time as the Hindus and Arabs did, and all of that was around the time of Christ's birth. I just think that's interesting that that happened there. I'm not saying there's some relevance there to that, just it's interesting correlation between those. Now, looking at some arithmetic symbols, like where'd your plus sign come from? Why do you use that to say I'm adding two things together? The most common modern arithmetic symbols, those include plus for addition, minus for subtraction, times or a dot, or parentheses even for multiplication, and then this line with a dot above and below, that's division. Most of those were first used in arithmetic and algebra in the 15th to 17th centuries. That's about when those happened. And plus and minus are also used to describe positive and negative numbers, like a plus 3 and a minus 3. So what did we say math is? Math is considered the language of science, right? It's a tool used to study God's creation. Like every language, it has its own symbols, like a plus sign and a minus sign and things like that. So if you haven't already, start thinking of mathematics like a language, and that'll help you not be so surprised when you see lots of new symbols and things. It's because it's a language. And you're going to learn many new symbols in Shormann calculus, and some of them, a lot of them will be reviewed though. You'll also see that using these symbols is faster than writing out words or phrases corresponding to each symbol. I mean, just look at plus, P-L-U-S. It's a lot faster to do that than to have to write the word plus every time, right? So when you see new symbols, just be patient. You'll memorize them as you practice, as you go back to the rules and definitions at the beginning of reading assignments and study those to try to memorize them. Well, moving on to part C on number sets and set notation. We'll start doing some examples now and refer to the lesson 1 rules and definitions for the different types or sets of numbers and the different kinds of set notation symbols. So just be prepared to answer questions like the one below, and you can pause the lecture, try to answer it if you're feeling confident that you remember all the number sets, set notations from Shormann pre-calculus or previous course. And I'll move quickly through these, but you have this lesson here to review in the e-learning campus, so you can click on that Shormann pre-calculus lesson. A lot of part C and D here are review from that. So example 1.1, true or false, no whole numbers are counting numbers. Well, let's just think about counting numbers. That starts thinking, count on your fingers, 1, 2, 3, 4, and so on. And whole numbers, those start with 0, 1, 2, and so on. So that's false. The only one that's not a counting number also from the whole numbers is 0. Example 2 on set notation, use a sentence to describe the set notation in each of the following and which choice there best represents the set of imaginary numbers. So that'll be the last thing we do after we look at A, B, and C. So in A, we have X is a member of the set of Z. That stands for integers. The vertical line means such that X is less than 0. So just write that out as a sentence. Then look at B. Y is not a member of R, the set of real numbers. That symbol means the set of real numbers. Y is not a member of the set of real numbers. And then C, Z is a member of Q. That stands for the rational numbers, a set of rational numbers such that Z is greater than or equal to 1. So just take some time, write those sentence forms out for each of those. And so here's the three of them. And so here's the three of them here, A, B, and C. Write those out. Look at this question too. Which of those best represents a set of imaginary numbers? So imaginary numbers are not real numbers. So that'd be choice B. That's representing, saying not a member of the set of real numbers. If it's not that, then it makes sense it would be imaginary if it's not real. Example 3, use set builder notation to describe the following, and this just requires familiarity with those set notation rules. And if you're not familiar at all, look at your rules and definitions. And so A, X is a member of the set of real numbers, so we can just go ahead and make our set brackets there. X is a member of that symbol, the set of real numbers, so big R there with that double line looking thing there, and such that X does not equal, so we'll put an equal sign with a slash through it, pi. That stands for the irrational number, which we'll talk about more in lesson 2, and we can just use the pi symbol, or if you wrote pi, that just how it's written there, that's fine also here. B, the integers are a subset of the real numbers. How would you describe that? Well, the integers, what's the symbol for that? It's that Z with that double bar right there. Z is a subset of, or are a subset of, so that's kind of sideways U with a line under it. That stands for subset of, and then the real numbers symbol there. And that's it. C, X is a member of the set of natural numbers. So put your symbol there. X is a member of the set of natural numbers. That's an N with that double bar right there. Set of natural numbers such that X equals 0. Now what are the natural numbers? Those are the counting numbers. Those start with 1. So this actually it doesn't make any sense. So we could have just written this as empty set, the 0 with a slash through it. That stands for empty set. That's an acceptable way to write that as well, because it's an empty set. There's no members of that set. Example 4, which of the following is a counting number? Think about counting numbers. It starts with 1, just counting on your fingers. Those are also natural numbers described as that. 1, 2, 3, 4, 5, 6. There's no decimals in there. There's no negatives. It must be this choice number 1 here, and so 1 only. Choice A. Problem 5, let's look at another type of notation, and this is fairly frequently used in calculus because we're thinking about graphing functions and looking at a domain or a range, a certain interval over which something works. And so interval notation is helpful there. And instead of using all the inequality symbols there, so A, X greater than equal to 0. So what we do there is it's greater than or equal to 0. We would put a brace here and a 0 there, and then say comma infinity. So X can be any of those things from and at 0 out to infinity, and infinity is a number increasing without bound. That's kind of a weird thing to think about, but just as we were talking right now, the value for infinity increased. So it's just always on the increase. So we can't close it off with a brace. That doesn't make any sense to do that. We put parentheses there because the parentheses represent that we're not closing it off, but we're at that value, just not equal to it. We're at it, but not equal to it. So B, X is kind of between -4 and 3, but it's greater than equal to, so we'd put a brace there and a -4, and then it goes on up to 3, and it's not like right before 3 or something. It's less than equal to, so since it's equal to, we put a brace there as well. And then C, X less than pi. So here it can be anything less than whatever pi is, 3.14, rounded to 2 decimal places. That's what pi is. So it could be 2, it could be 1, it could be -6,000. So we'll say parenthesis minus infinity, because it can go all that way. It's x is just less than that, and it's not equal to pi. It's super close to pi, we could say, but it's always less than. So we put a parenthesis there too, just to say that we're not including pi, we're just including just to the left of pi, just a little bit less than pi. That's an important part of calculus too, that closeness to a value but not equaling the value. That's called an infinitesimal difference, and so that difference between putting a parenthesis there and a brace there, that's a huge important thing in calculus. Moving on to part D now, in special number types and exponents. One thing we're going to focus on here is just comparing normal base 10, tens place, ones place, 1/10ths place, hundredths place, things like that. That's what base 10 means, so that's what you're used to. That's what you've been doing since elementary school aged curriculum. Thinking about place value, there's 10 to the 0, the ones place. 10 to the 1 is the tens place. 10 squared is the hundreds place. 10 cubed is the thousands place. 10 to the minus 1 is the tenths place. 10 to the minus 2 is the hundredths place, and so on, to the left and to the right on that. You can see as you move from one place to the next place to the left is 10 times more than its place to the right. So now think about another type of base system, like a base 2. Look at base 2. It has 2 digits in it. Base 10 has 10 digits from 0 to 9. Base 2 has 2 digits, either a 1, we can think of 1 as on, or 0 as off. And it's used in computers because computers run off electricity, and electricity is either on, 1, or off, 0. If you did Shormann Precalculus or Shormann Algebra 2, you know about truth table. Something is either true, 1, or false, 0. So like a base 10 place value, base 2, as you move from right to left, each place increases 2 times more because it's base 2. If this was base 3, it would increase 3 times more. If it was base 4, it would increase 4 times 4. But all we're doing is base 2. And so as you move from right to left, it increases 2 times more. So you see that 2 to the third is 8. What's the next one? It's 2 times more. 2 to the fourth, 16. How do you get a computer to think of a 9 if all it works off of is on or off, ones and zeros? You have to convert from base 2 to base 10 or vice versa. So let's do that. If this is the first time you've ever seen binary numbers, don't worry about it too much. What is this course titled? It's titled Calculus. Calculus is the most important thing, and you might want to make a note of this. That means things that are related to limits, derivatives, and integrals. Lessons about those are your priority. This is a low priority thing. Don't panic about it. Don't freak out about it. Give yourself time. Be patient. You'll figure it out. So look at A. How do we convert 1001? That's a binary number. That's what this problem says. That's a binary number. Convert it to base 10. Well, we can look at our place value there, our placeholders, and the powers that are underneath them. And let's just think about this. Here, we'd put a 1 here in the ones place. And so this is like the twos place. There's a 0 there, so it's off. And this is off, and then the 2 to the third is on. And so then what we can do down here for A is we can say 1 times 2 cubed is 8, plus 0, because that's off. 2 squared is off, plus 0 times 2, plus 1, because this one's on. 2 to the 0 equals 1. So we have 8 plus 1 is 9. There's our answer. That's the base 10 version. If you want a calculator or a computer, you want to program it to read out a 9, you have to put it in as binary, as 1001. B. And of course that's for programming a computer, making it present stuff on the screen in the right way. Look at B, 101.01. So we have 101. That's like 2 to the 0, 2 to the 1, 2 squared. 2 squared is our biggest place right here, and it's on. So we'd say 1 times 2 squared is 4. Plus 0, that's off, times 2 to the 1 is 2. Plus 1, that's on, times 1, 2 to the 0 is 1. And then plus 0 times 1/2, because 2 to the minus 1 is 1/2, plus 1 times 1/4, or 0.25. So then we end up with a 4 plus a 1 plus a 0.25 is 5.25. C. Maybe pause the lecture, see if you can do this one on your own. We'd have 1, 1, 1, 0, 0. So we have 2 to the 0, 1, 2, 3. 2 to the 4th will be our biggest place there. So we'd have a 1 times 16. That's on, plus 1 times 8, plus a 1 times 4. And the rest are off. I mean, you could write them all out if you want to, or just understand that the rest of them are going to be 0. And we just have a 16 plus an 8 is 24, plus another 4, that's all 28. That's what that equals. 11100 in binary is 28 in base 10. Let's go the other way now. Example 7, convert the following to binary. So for A, we've been given a base 10 number of 8. And so in your placeholders chart here for base 2, do you see an 8 in there? Well, yes, right there. So that would be on. And so we'd say 1 times 8 plus 0 times 4 plus 0 times 2 plus 0 times 1. And we don't have to put the decimals because those are all zeros also. So it would just be 1, 0, 0, 0. So we don't say that like we would base 10. We don't say 1,000. We just say 1, 0, 0, 0 because that's how we read that binary. You have to think about it in terms of on and off. Which places are on, which places are off. It's base 2, so there's only 2 digits. Base 10 has 10 digits, right? 0 through 9. Look at B. And look at C. I mean, we're just going from 8 to 8.5 to 9. So do you see in B, we already know what 8 is, but what would the 0.5, how could we add half to that? Well, that would be the 2 to the minus 1, right? That needs to be on. So really all we're doing then is saying 1,000.1, because that would be an 8 plus a 0.5, right? And then C, 9, well, we know 8 is at 2 to the 3rd. We just need to add 1 to that, which would be the 2 to the 0 place, right? So this would just be 1, 0, 0, 1. And that's it. So again, binary is used in computer programming, and for example, you might have a computer and you can look at your display color and your color quality. It might say that it's 16-bit color quality. That means there are 2 to the 16th possible colors that could be displayed. So moving on to some other number types here, just reviewing absolute value and imaginary numbers and factorials. So like in A, we have a 3 factorial, which means 3 times 2 times 1. You can use your factorial button on your calculator if you want. Or like that one's easy enough, just do in your head 3 times 2 times 1 is 6. And so we can simplify in some steps here. Minus 7 and then plus absolute value of negative 10. That'd just be a 10. And so then 6 and a negative 7 is negative 1 plus 10 is equal to 9. B, we have some square roots there, and so a good idea with square roots is to break those up into factors that you know the square root of. Like the square root of 16 is 4, the square root of 25 is 5, square root of 36 is 6, things like that. So with an 80, a square root of 80, maybe you know you could break that into 8 times 10, but there's no square root there. What about 16 times 5? Yes, we can do that. And we're doing 16 times 5 because there's a factor there that we know the square root of already. So we'll say square root 16 times square root 5 plus the square root of 5, which we can think of as 1 times the square root of 5, right? And then 3 times square root of 3 on the outside. So notice what we're doing on this problem. We're simplifying inside the parentheses first, simplifying that square root down some. Square root of 16 is 4. So what we really have there is 4 square root 5 plus 1 square root 5 is 5 square root 5. Parentheses means times 3 square root 3. So multiply the two numbers together. 5 times 3 is 15. Multiply what's inside the square root sign. Square root 5 times square root 3 is square root 15. We can't simplify that anymore, so that is our answer. C, I equals square root of -1 in these problems, so that means I squared equals -1. So when you see an I to the third, I to the fourth, I to the fifth, break those into I to the squared pieces, and then you can change those to -1. So 8 I to the fourth is like I squared times I squared, or -1 times -1. Minus 14I plus 12. So then we have that would just become a positive 8, right? And we'd have 8 and 12 is 20. So we write the real part first. Remember, on a complex number, the standard form is a plus bi, the imaginary part second. So 8 and 12 is 20 minus 14i. D, recognize the complex conjugate there. 6 plus I times 6 minus I. So we'd have 6 squared is 36, and then we'd have a 6i and a minus 6i. Those would cancel. Then we're left with a minus I squared on the end, or minus times a -1 is plus 1 equals 37. Last, let's simplify some exponential forms, looking at things pre-algebra 1 level that maybe you still make mistakes on. So A, the opposite of, you got to think of that as the opposite of 3 squared. So you do 3 squared, which is 9. The opposite of 9 is what that is. B, the instructions say write an answer as a number without exponents, but this isn't a number, so we'll just leave the exponent there and simplify it by making that positive. Minus 1 over x squared. The opposite of x to the minus 2 is minus 1 over x squared. That's how we could simplify that. C, that's minus 3 times minus 3. That's what that means. When it's in parentheses, that negative's in parentheses, we just, if it's squared, that means we do it twice. If it's cubed, we do it 3 times, and so on. So that would be a positive 9. Notice the difference between A and C. And then D, there we can just simplify that to 1 over, again, watch those parentheses, minus x squared. So there we have a minus x times a minus x, which we could just say is 1 over x squared. So notice the difference between B and D. B is the opposite of 1 over x squared. It has that minus sign out front that you could just put your finger over to cover it up and perform that operation. When it's inside parentheses, though, we can't like cover it up. It's grouped with that, so we have to keep it with it. We have to think minus x times minus x. And one more problem with some fractions, and it's simplified to eliminate all unnecessary exponents. So similar bases multiplied together, you can add the exponents together. And order doesn't matter in multiplication either, right? So we could rearrange this, and we could have 3 to the minus 2 times 3 to the 4. So we get the same bases next to each other, times 4 squared. Similar bases multiplied together, we can add the exponent. So we can add a minus 2 and a 4 to get a positive 2. And so that would be a 3 squared times 4 squared. So there we go. B, 4 squared over 5 to the 6th. And what we can do here is take that and multiply it by the terms on the inside. And we can also make this 4 to the minus 4 into a 1 over 4 to the positive 4. So We have the 4 squared, multiply it by the 5 in 5 squared, over 5 to the 6th times 4, minus 4 squared over 5 to the 6th times 1 over 4 to the 4th, we'll say. And so then, just looking at each term here, and we're not simplifying down to a number, we're just simplifying to eliminate unnecessary exponents. So this is a 1 right here, right? It's understood if there's nothing there that it's a positive 1. So I have a 4 squared over 4 to the 1, which is the same thing as 4 to the 2 minus 1, right? Hopefully you can do that in your head by now, and you just put a 4 there in the numerator, and then we have a 5 squared over 5 to the 6th, which would simplify to 5 to the 4th. Minus 4 squared over 4 to the 4th, we can just make that a 4 squared in the bottom and have 5 to the 6th times 4 squared. And that would be our simplified form. That's all we have to do on that. And that is all for lesson 1.